Hello everyone. Today I would like to show you a practical application of deep learning for demand forecasting, as well the use of reinforcement learning on time series data here for inventory decision making. This is a extension of VN2 competition. And let me start with a very short introduction of the competition itself, because not everyone may have followed it before. In the competition, we have around 3 years of history of weekly data, almost 600 time series at the store product level, including historical sales and information about product availability. In addition, during the competition, each week we know how much inventory is currently in each store, as well the deliveries that are already scheduled for the next 2 weeks. The key point is that we make the order today, but the goods arrive only 2 weeks later, which means that they will affect the sales starting from week T+3. So the goal here is not the forecast alone, but the cost minimization on one side from the holding and on another from the shortage. So from a business perspective, we are not asking how good the forecast is. We are asking which decision leads to the lowest cost. If you are interested in the competition itself or the winning solutions, there was a session where the organizers explained the competition in details, and the winning teams presented their approaches. The recording of the session is available online on YouTube. My solution won the VN2 competition, and it consisted of 2 stages. Stage 1 was a global model based on an ML estimator, specifically cat boost, used to forecast demand 3 weeks ahead. Stage 2 was an ordering policy that take that forecast, the current inventory state, information about already scheduled deliveries, and then generate a cost-aware order. An important point is that what won the competition wasn't deep learning. It wasn't even reinforcement learning. It was a well-optimized policy built on accurate forecast. Today, however, I'm not going to focus on my winning solution, but if anyone enjoys more technical details, I described the architecture and reasoning behind it in more fully paper that is available on Arxiv. The solution that actually won was supposed to be only my internal benchmark, something better than the competition benchmark, but for sure not the final target solution. The real target solution was meant to be a neural network, but I only finished it after the competition ended. So this is exactly the deep learning based approach that I'm going to show you today. And let us start with the forecasting part based on deep learning. And here you can see the architecture at the high level. For now, there is no need to focus on each individual blocks because we will go through them on the following slides and break them down into smaller parts. First, let us look at the inputs and outputs, and let me actually start from the end. So the network generates the point forecast for the next 3 horizons. So the output is a 3-element vector. To make that forecast, the network needs to receive as the input the vector of the last values of sales of the length context length, and then another vector of the same length with Boolean values indicating whether the product was in stock or not. So let's assume that the context length is 20. So the network receives last 20 sales value and the matching information about whether the product was in the stock or not. In addition, it receives so-called static covariates, namely store and product ID. So the network knows for which combination it generates the forecast. And the last information is week number, the last week number from the context. This tells the network where we are in the year. So it can take into account the seasonality, of course, if for a given specific time series exists. Before going to the network details, let us first look at how the inputs and outputs are prepared, both for training and inputs for inference. So for each time series, I'm building sliding windows. So I take the last 20 sales observations as the context, together with binary information about whether the product was in the stock, and corresponding information about number of week and static covariates like product and store ID. The forecast horizon is free, so the target is the three next values after the context, meaning values after X. A very important element here is the dynamic scaling. Instead of training model based on the raw values, I divide both input and target by a scale factor computed from history. The scale factor is equivalent to the sum from the previous year, excluding the weeks that were affected by the stockout. Thanks to this scale factor, one global model can learn from both small and large series, at the same time focusing on patterns in the data rather than absolute scale of a given time series. In addition, X is standardized, but that is done only for training stability reasons. During training, I apply augmentation. This is a well-known technique. The full implementation is written in PyTorch, and here I use what PyTorch already provides. Two modes, train and eval. This allows the network to behave differently during the training and during the evaluation inference. So during the training, it can behave stochastically, and some behavior are turned on, like dropout or augmentation, but during evaluation and inference, the network works in deterministic way, and of course, augmentation and dropout are turned off. I said that I use augmentation and it's a well-known technique, but you could ask me why at all we want to use augmentation. First, because this data set is quite small, 600 combination with around 3 years of weekly history. But even if we look at the forecasting more generally outside this specific data set, time series data is usually limited with NLP or computer vision. So without augmentation, the model can very easily memorize specific weeks, specific IDs, or very specific cases. Thanks to the augmentation, the model can better generalize and better deal with future or even imperfect data. Here you can see which operates happen step by step for network inputs. First, scaling based on this dynamic scale factor, then standardization, where the mean and standard deviation are only computed from the trained set. And next, we move to augmentation. The key point is that the augmentation is not applied to all store product combinations. So for each observation in the batch, we randomly decide whether augmentation will be used at all. So some examples pass through the model during training unchanged. So thanks to that, the networks during the training see both clean, meaning in that context, unchanged data, and slightly perturbated. Also, you can see different types of augmentation, and these augmentation types are independent. So it means that during the training, one of them can be applied, two of them, or sometimes even all of them. The first one is time augmenter, which slightly rescale the series of the context, of course, not the entire series. Mask random fragment of the series and replace that mask fragment with the median of that context. And finally, add some random noise, but without changing weeks affected by stockout. Next, we have this week augmenter, which shift the week number by 1 or 2, so the network doesn't become too attached to a very position in calendar. Then you have this static covariate, which replaces the store and product ID. In my implementation, I replace this ID with another available ID, but a good idea is to replace them with ID 0, meaning unknown. This gives us an extra advantage. So if a new store or product appear, we can still generate the forecast without retraining the network. And finally, I apply dropout to the input. We have already gone through the inputs and output, what they are and how they are prepared for the training. And now let us move to the architecture details, and let's start with embeddings for static covariates. So embedding is simply a learn table of vectors. So each store and each product gets its own vector, which becomes a learned representation of that entity. So thanks to that, the network can know that some products share similar patterns like trend, seasonality, or other patterns if exist. The same for the stores, of course. The context, meaning the recent sales values and stock availability, are concatenated together, creating a matrix of shape 2 by context len. The matrix is then passed into the TCN block, meaning temporal convolution network. As I said, the input for TCN is already the matrix, but we can also think of it as 2 channels arranged as a tensor of shape 2 channels and time, where the channels are sales history and product availability, meaning stock. The first operation is the input projection through convolution. And here is one important detail. So the convolution doesn't yet look a long time. So it's not learning trend or short-term temporal patterns. It operates on each time step separately, but it looks at both channels at the same time, meaning sales and stock in the same week. So for each week, the input projection take the pair sales history and stock and transform it into a richer hidden representation. So we move from 2 channels to hidden channels, for example, 64. Then this projected input is passed into a stack of several TCN blocks, one after another, where each layer takes the representation from the previous one. The main difference between these TCN blocks is the value of dilations. If we zoom into a single TCN block, it consists of 2 causal convolution layers. And after each of them, we have normalization, GELU as function activation, and dropout. At the end of the block, we have also residual connection, and it's important because the next layer doesn't receive only transform signal, but it receives the sum of the new representation and original one. Because of that, the new block doesn't need to rebuild everything from the scratch every time. It can learn only a useful correction to existing representation. And this stabilizes the training, of course, but also it helps preserve the information from the previous layers. At the lowest level, we have this causal convolution. It works like a standard one-dimension convolution over time, but with one restriction. At the given step, it can only look at the present and the past, never at the future. The individual TCN blocks differ in the dilations, as I said, the parameter. And here I wanted to give you the intuition about why different dilation values are used one after another. If I used only a standard convolution everywhere, then each layer would look very locally, mainly at neighbor weeks. That is good for capturing short patterns, but weaker for building broader context. That is why in the following blocks, the relation increases. For example, 1, 2, 4, 8. The intuition is that the network builds the representation hierarchically. With the same kernel size, each next layer look wider and wider into the history. So the first layer will learn short-term patterns. The next one combine them into longer dependencies, and the whole stack produces the representation what covers almost or exactly the entire historical window. So instead of looking at the entire history with one large filter, we build the picture step by step from local signal to broad context. And as I said, that the final timestamp of the representation already contains information from the whole context, I simply take the last value, and this last value is compact summary of the history, and it becomes the output from the TCN. Okay, so right now we already have two things. First, we have a representation of the temporal context built by TCN from the sales history and stock information. Second, we have store and product embeddings, meaning information about for what time series we are generating the forecast. Now we want to combine these two information. Okay, but you could ask me why at all we want to combine this information, because context alone is often not enough. Two time series may look very similar over last few weeks, but one of them can be regular and stable, while the other one can be heavily depend on other factors like weather, promotions, price changes, and so on. So from the perspective of recent history, they may look very similar, but from the business perspective and in terms of future values, they can be very different. So I want the model to be global because that allows the knowledge transfer across time series. But at the same time, I want to learn the identity of stores and products through static covariate embeddings. Okay, so we already know that we want to have these two informations. So how to combine them? So maybe just concatenate TCN output with embeddings, and it should work, right? We will have just one vector with both information. Technically, yes, it works, but also it has an important drawback. In that setup, the network gets a very easy shortcut. It may start treating embeddings as the main signal and partly memorize the typical behavior of specific IDs and stop analyzing and take into account the information from the context. So with a small number of time series, the risk is especially high because it's easy to fall into the memorization problem. And there is where the film comes in. Film feature-wise linear modulation. So it combines both types of information, but in the way that they reduce the risk of overfitting through memorization of specific static IDs. Based on concatenated ID embeddings from store and products, it creates two parameters, beta and gamma. And these parameters are then applied to the context representation built by TCN using a very simple formula. So the TCN context vector multiplied by gamma, where gamma is in the range from 0 to 2, and then plus beta. And that is why it is called modulation. So I modulate the context itself. So gamma tells the model which dimension of the context representation should be strengthened or weakened, while beta allows a small shift of the representation in the direction that is more suitable for a given time series. After the context modulation, we move the decoder. That is a standard multi-layer perceptron that returns 3 values for the 3 forecast horizons. Since the forecast horizon is only the next 3 values, using 3 output neuron is not problematic. Still, if the number of horizons would be larger, it would be worth considering another strategy for multi-output horizon. At the end, I use soft plus activation function so that the forecast remain non-negative. This is important because negative demand doesn't make any sense. Also, the target during the training, target is raw value divided by scale factor. So this kind of activation keep the forecast consistent with the nature of the data on which the model was trained. So far, the network hasn't received any direct information from which it could infer seasonality patterns specific to the week where we are, right? Someone may say that we could simply extend the context length in order to let the model infer seasonality from the context. But okay, it can work, but it would mean adding many extra values just to capture what happened 1 year ago, 2 years ago, and so on. So let us treat the context as a way to model short-term patterns. Trend comes partly from the context and partly from the embeddings that were used to modulate the context. To account for seasonality, I'm adding extra branch called seasonal head. It doesn't try to predict future demand by itself. Instead, it tries to answer the question for this store product pair and for future weeks, should the forecast be seasonality adjusted up or down? So now let us move to the details of this seasonal head, what produced this seasonal factor, what later will adjust our forecast up or down. So input for this seasonal head is the week number, more precisely the last week from the context. For each forecast horizon, I create a full set of seasonal Fourier features, casines and casines with different hierarchies. So for T+1, T+2, and T+3, I create a set of seasonal bases that describe the cyclic behavior. The second input is vector of concatenated ID embeddings, and based on them, I generate seasonality parameters for the specific series. Exactly, coefficients or parameters A and B, which determine how strong each sin and cosine should be used, and gate, which decide whether the seasonality for the series should be strong, weak, or almost null. So idea here is that the seasonal basis is shared because it comes directly from the week of the year we are, but the where it is used is specific to the given store and given product. It creates this seasonal factor, what then adjusts our forecast. So at this point, I already have the network, so the next step is to train it. The loss function is masked Huber loss. Huber is more robust than two outliers than MSE. I compute the loss jointly for all 3 horizons, and the very important part is that I use a mask. So the model is not penalized to weeks, for weeks what were affected by stockouts. For optimization, I use Adam W. We can skip the training, but I think that all of the details are described here. And the data is the data split is designed in the way to not have time leakage. So the test set is exactly the same weeks corresponding to the competition simulation. The validation set is the 8 decisions weeks right before the test period. The training set is everything earlier. I monitor the lost metric both on the training and validation sets, and I use the validation value for early stopping. At this point, we already have trained demand forecasting network, right? But then really, I ask myself, can I still do something more without changing the architecture? You know, can I do something to even get better results after that training? And yeah, I found a simple way to improve and already train the network. Maybe there is more ways of doing this, but I found one, and it's really simple. And remember that the network output is scaled value, and the loss was also computed on scale values. And this is a very good approach because the network mainly focuses on pattern in the data rather than absolute level of individual time series. Now I move to the fine tuning. So with a small learning rate, I continue the training, and the network output still is scaled value. But right now, the loss function is based on the scale value. Why is it important? Because in business, an error on a high volume product usually costs much more than the same relative error on small time series. And there is one more thing happening here, something that is not obvious at the first glance. The embeddings also receives information about the scale level associated with a specific ID. And this information, it will be for us important later, but you will see. Okay, you have probably been waiting for that slide, maybe not that one, but the next one from the beginning to answer how good this network is comparing with other approaches. For a moment, I will answer you. We are almost here, but I wanted to tell you once again that the test set is the same test set as the competition one, and this is important, and we need to remember about it. So, and here we have the test set results. So deep learning performs better, but the advantage doesn't seem huge. I will come back to this topic later, but we can already see that greater complexity doesn't always lead to proportionally greater gain. Okay, now let us move to the second part of the solution, what is making orders using reinforcement learning. So the ordering problem itself can be naturally described as Markov decision process. We have a state, meaning the current inventory, the in-transit information, forecast generated, right? Then we have the action, meaning generation of orders. And finally, we move to the next step, next state after one more week of sales is realized. This reflected in reward, what for us is simply the sum of negative holding and negative shortage. Before we move to the final architecture, let us start with a short introduction. If we simplify things a lot, but a lot, we can say that reinforcement learning has two main approaches, policy-based and value-based. In the policy-based approach, the model learns the policy directly. We can say that it creates something like a map between the state and the action. In the value-based approach, the model doesn't immediately say what to do. Instead, it first evaluates how good a given action is in a given state. So it learns a value function, and the final decision is chosen based on the highest score. And for me, for this problem, the policy-based approach feels natural here, because we have a given state, and based on it, we want to decide how big order should be. And also the second thing is that here, decisions is continuous, because we need to provide the number of the order rather than discrete. The simplest example of a policy-based approach is reinforce. Here, the model learns the policy directly. So it receives the states, generate the action, execute this action in the environment, observe the reward, and update parameters based on the outcome. The intuition is simple. If a sequence of decisions led to a higher reward, we want to increase the probability of making similar decisions in the future. If it led to pure result, we want to decrease that probability. What the model output is, it depends on the type of the action. If the actions are discrete, the model usually returns probabilities of individual decisions, for example, through softmax. If the actions are continuous, as in my case, the model returns parameters of the distribution. For a normal distribution, it will be a mean and standard deviation. And here, important note, the policy doesn't have to return one fixed action immediately. In fact, we don't want to do it during the training. And here, go back to the slide about two modes, training and versus eval. During training, we want exploration. So the action is sampled from a distribution. In eval mode, we want action to be deterministic. For continuous actions, we will take them in if the distribution was normal. For discrete actions, we take the action with the highest probability. But, however, reinforce has one major drawback. The learning signal has a lot of noise, and it's really difficult to separate that noise from the real signal. Let me explain it more simply. The network learns based on the final effect of the whole trajectory. In other words, the whole episode. In a chess example, the whole trajectory would be one full game, where the trajectory is a sequence of states, actions, and rewards. But also we need to remember that we are creating solutions based on real world data, right? And world is not deterministic. There is a lot of noise. And if we only observe many full trajectories, it is hard to tell whether the reward truly came from one specific decision or rather from randomness and from the rest of the episode. That is why reinforce is good as a starting point. It's good to understand the idea, but we need to adjust somehow to not have this drawback. Okay, and here we have actor critic, what combines these two approaches. On one side, we have the actor, which is the policy-based part that suggests which action to take. On the other side, we have the critic, which is the value-based part that evaluates how good the current state is. Thanks to this, the actor no longer learns only from the entire episode or the effect of the entire episode. It gets the additional signal from critic, and this signal is corresponded to the specific action and state what it took. So this makes the policy update more local, more informative, and less random, and not only based on the entire effect of the whole episode. Okay, and here I'm using PPO, proximal policy optimization, but I'm not going to go into the details what PPO is, because I want I don't want to describe all of the details of the architecture. More, I want to focus on the network architecture. Here the PPO, because you can find in the internet what it is, or maybe in another session I should describe it in more details. Okay, so now let us move to the architecture details for reinforcement learning used for this decision making. I will describe it similar as I did for this demand forecasting network, but here you can see that for input we use the forecast generated by previous network, static covariates like store, product ID, also week number, and also we are using here state information such as the on-hand quantities and in-transit quantities. Important point here is that inputs like predictions and state information are scaled by the scale factor, but still the network already knows about the magnitude for a given time since. Why? Because here we are reusing layers from demand neural network like embeddings and seasonal head. But here, these layers are already trained and frozen during the training, right? The network output consists of two actions. Based on this, we will generate the final decision, but I will describe it in the next slide, what these actions mean. So the agent doesn't need to generate the order completely from the scratch. We can help it because we know the physics, right? And also we know the relationships between weeks through inventory projection over the 2 weeks. So at the input, we have the current stock, what means on-hand value, in-transit deliveries, and forecasted demand. First, we compute how much inventory should remain after the first week. Then I do the same for the second week. Based on it, we can calculate something what is called here base order, meaning the baseline order for week 3. And only at this point, the reinforcement learning policy step in. It doesn't return the final order. Instead, it returns two consistent, two continuous actions. So the first one is multiplier, which scale the base order up or down. The second is the additive buffer. And the second component is important because if only the multiplier existed, then when the order, base order is 0, the agent wouldn't have a way to adjust it. Buffer gives the agent flexibility. Now let us move to the architecture details and start with operation of building a graph or building graph nodes between future weeks. Okay, each node represents information for one of the future weeks. Before I go into the details, you may ask, why at all I want to use graph instead of just putting everything into one plot vector? The reason is that the future weeks are not independent. What happens in week t+1 affects t+2, and that affects t+3. Also, I don't have all information about these weeks. Often I rely only on the forecast, and also I need let the network to learn how much uncertainty comes from the forecast error, because the larger forecast error is, then probably larger buffer should be. I have 3 nodes because my decision horizon covers 3 future weeks. Each of them describe the inventory and demand situation in a given step. A single node contains 6 information. Starting inventory, meaning the inventory level at the beginning of that week. And here you can see that for the first node, this value is known, but for the following nodes, this value comes from projection. So it already includes some uncertainty. Then the second one is transit, meaning what arrived from already placed deliveries. Important. For the last node, this value is 0 because the node corresponds to the result of the order we want to making through this network. Then we have this forecasted demand for a given week, projected an inventory, projected shortage, and also information from the seasonal head. These nodes now need to be transformed into a vector representation. Okay, so the numerical node feature pass through a linear layer into the hidden state. Then we add a step embedding, so the model knows whether it looks at t+1, t+2, or t+3. It's important because, as I said, even we have the same variables in these nodes, they are not the same because, for example, starting inventory is not known for node t+1, but it isn't not known for t+2 and t+3 is projected. So there are some uncertainty. Also the same topic for in transit. We don't know how much in transit it will be for the last node, okay? In addition, I also add this projection from embeddings. So thanks to this free information, each node contains at the same time the inventory physics, the position in the decision horizon, and identity of the series. So once the nodes are embedded, we pass them through the chain graph. And the input to the chain graph is this node embedding, meaning the vector representation for the 3 future weeks. So in other words, here is a matrix, right? The role of the chain graph is to make sure that the network doesn't look at each week separately, but instead understand the dependencies between consecutive weeks. In inventory planning, it's important because, as I said, the situation in t+1 affects t+2 and so on. And after passing through the chain graph, I take the last node because it already contains the summary of the whole chain. For a moment, I will describe why it already contains this summary. And this representation is used then by the value head and the policy head. The value head is the critic, it evaluates how good the current state is in perspective of future reward. The policy head controls the policy and generates these two actions. Earlier, I said that the final node after sequence of chain graph layer already have the summary, right? Based on these all nodes. Okay, and this summary is created through chain graph layer because, okay, let's go step by step, okay? And let's first focus on the first chain graph layer. So each node combines information about itself with information from the previous node. So week t+3 receive its own local context together with the signal coming from t+2. This is done through a residual connection. So the model doesn't lose the original information from the node, but only adds a useful correction to it, okay? And let's imagine that right now we are in the second or even in the third chain graph layer. So node t+3 already contains information from t+2, and t+2 contains information from t+1, and so on. So with each additional chain graph layer, the nodes becomes more and more enriched by information from the previous nodes. That is why the last node becomes a representation that already captures the whole sequence. Okay, now let's look how reinforcement learning is trained. So first, I use already trained demand model to generate the forecast for the next 3 weeks at each step. Then for each epoch, the simulator sampled the episode start and also sampled the initial inventory state because we don't have historical data for inventory states. Then third step, based on the state, based on the forecast, we build the observation input for the agent. Step number 4. Next, we execute the policy. Yes, we execute the policy in training mode, meaning we perform a rollout where the action is sampled. 5, the reward is consistent with the competition. Setting 6, we collect trajectories, compute the loss function, adaptate the agent weights. The last step, the trained agent is used in a deterministic way on validation set, and this validation set serves for early stopping. Here you can see the results on the test set for reinforcement learning, my winning approach, and for the competition benchmark. In addition, for the first two methods, the cost reduction related to the benchmark is presented. And maybe the most important slide here. For both, the results are better in terms of forecast quality and in terms of total cost. However, the data set is quite small and the test set is short. So being honest, the better result may simply be far. That is would be worth testing at least this demand network on larger data set, popular benchmark data set like N5 competition. I have started it because I have also started writing a paper about it. So also I need to test it on other set as well. A second is more practical because the solution is very complex, but the results are only slightly better. So natural question is the extra effort really worth it? So I would say that it depends, because if we are working in a small company for smaller project, then probably it's better to start and end with something simple and quick to implement. But if we are working on a global project for a global company where 1% improvements translates into savings worth millions, that is probably worth the effort. So here there is no one single universal answer. Thank you for today. If you have any questions, please leave comments or ping me on LinkedIn. As I said, I'm starting writing the paper, so maybe if you see or watch it, and this paper is already available. Thank you for today. Bye.